morning all. Today we are coming with another topic, that effect of dielectric on capacitance. So we have already discussed the dielectric behavior of conductors and the capacitor, the basic principles of capacitors and their effect on the conductors and the capacitance. So in this session, how we can modify the capacitance of a parallel plate capacitor when a dielectric is present. So as we have seen, we have two parallel plate conductors. They are charged with positive charge Q and negative charge, and also their area is A, and they are separated by a distance D, and the surface charge densities of these two conductors are plus sigma and minus sigma respectively. So for our convenience, we consider that the vacuum is present. Vacuum is the medium in between these two plates. So therefore the electric field produced can be taken as E naught. E naught is the electric field produced in between these two regions, or the region of between the two plates. So that is equal to sigma divided by epsilon 0, and epsilon 0 is the electrical permittivity of vacuum. And also this is the potential difference between these two plates can be taken as V naught. So the potential difference can be then written as per the equation, E naught is equal to E naught into D. That is D is the distance separated by them. So now the capacitance of this conductors C0 can be written as Q divided by V naught. That is the potential difference between these two plates, and that is equal to, we can write as epsilon 0 into A divided by D is the capacitance of the parallel plate capacitor. Now consider that a dielectric is inserted in between these two conductors, and they are inserted in such a way that they fully occupy the intervening region between these two parallel plates. Then when it is inserted in between these two plates, what will happen? The dielectric will be polarized. It is polarized due to the field present in that region, or the effect is equivalent to two charge sheets with surface charge densities. Okay, the surface charge densities of the dielectric inserted will be plus sigma polarized and minus sigma polarized. So that will be the surface charge densities of this dielectric inserted. The net surface charge density will be plus or minus sigma minus sigma p. It is the difference between the surface charge density of the parallel plate capacitor and the surface charge density of the dielectric inserted. So therefore E can be rewritten as the electric field. What will be the net electric field produced? That is the sigma. Instead of sigma we will write sigma minus sigma p. That is the surface charge density of polarized dielectric divided by epsilon 0. So that the potential difference between them, the potential difference across the plate is also can be written as V is equal to, as per the equation, V is equal to E into D, sigma minus sigma P divided by epsilon 0 into D. The difference between this surface charge density of parallel plate capacitor and surface charge density of polarized dielectric is proportional to the sigma, that is the surface charge density. So, and we can write as, so what we can write, the sigma minus sigma P is equal to sigma divided by K of the dielectric. And clearly, if K is the constant of dielectric, and whose value is k is always greater than 1. The potential difference V is equal to, in terms of the constant dielectric, or it is known as the dielectric constant. So V can be rewritten as here sigma divided by epsilon 0 into k into d. So that can be written as, the value of sigma can be substituted in this equation, so that we can get q into d divided by a into epsilon 0 into k, where sigma is equal to q by a. So now therefore the capacitance of the dielectric C can be written as, C is already we know that q divided by V. So now we can write the value of V is equal to q into, what is the value of V? Q divided by q into d divided by a into epsilon 0 into d, sorry, k. So the q and q will be cancelled, so the value will be obtained as a into epsilon 0 into k divided by d. So here the term epsilon 0 into k, product of the electrical permittivity and dielectric constant, and this term is known as permittivity of the medium, and which is denoted by epsilon. So therefore we can rewrite this equation A divided by d into epsilon, where epsilon is equal to epsilon 0 into k. Consider that the medium, for medium vacuum, the value of k is equal to 1. Okay, for k is equal to 1, and at this condition what will become value? The value of k is equal to 1, the epsilon. So we have epsilon is equal to epsilon 0 into k, and for value for a vacuum k is equal to 1, then what will become? And the permittivity of the medium become the permeability of vacuum. So therefore we can get the value, therefore the value of k is equal to epsilon divided by epsilon 0. This is called the dielectric constant. So the dielectric constant k is the ratio of the permeability of the medium, electrical permeability of the medium, and the permittivity of the medium. So which is different for different medium.